All right, we're going to take another look at the problem we were looking at in class. We're going to do this two ways, at least two ways. We might have a third way. I'll explain the third way, and we'll see if that math works out naturally enough that it warrants going over it. But here's our basic setup. We've got to cross a 2-mile wide river, and we've got to go 9 miles downstream, laying pipe along the way with this cost function that tells us we're going to spend $8 for every length of pipe going across the river. We'll call that y. So 8 times y plus $4 for every unit, every length unit going downstream. We'll call that x. So the question is, how do we minimize our cost? Now, we saw in class some good back of the envelope calculations, right? So one candidate solution would be cross straight and then go this way. Let's think about what that would do. You'd be spending 16 for this part, plus 4 times 9 is 36. 16 plus 49, well, let's see, I should be able to do this faster. 16 plus, did I say 49? Not 49. 4 times 9, which is 36, which is $52, or $52 million, or whatever this 8 represents. So 52 is one possibility. We also saw that we could just cut straight across, in which case we're looking at the square root of 2 squared plus 9 squared, which was really just the square root of 85, which I'm going to calculate really quickly, is 9.2 times 8, which gives us 73, right? So going straight across is not going to be what we want to do. It would be cheaper to go straight and then turn at a right angle. But something else to be aware of here, and this is sort of the third approach that we might think about here, is as we extend this length, right? So we've got some length here. We'll call this, let's call it z. So z plus x equals 9. But if z is, say, 1, right? So if z equals 1, then y is going to be a little bit longer than 2. But we're going to be saving $4 for that bit of pipe. So our marginal benefit of increasing the length of z is we save $4. The marginal cost is we're going to have $8 times however much longer y is than it would be if we just went straight across. Let's see what that is. 2 squared plus 1 squared, that's 4 plus 1. So y is the square root of 5, which is square root of 5, 2.23. So we're adding less than a quarter of one length unit, which means we're adding less than $2 if z equals 1. So adding 1 unit to z means we save 4, we spend 2, that's $2 a profit, right? So we know for sure we don't want to just go across and then 9 miles down. We know for sure we don't want to go straight across the square root of 85 all the way in a straight line. The truth is going to be somewhere in the middle. Right, so let's just lay out, since we brought it up, that marginal cost, marginal benefit of z. Right, so the marginal benefit of z, of making this length greater, of angling across the stream so that x can be shorter, the marginal benefit is just going to be 4 times however long z is. Right, so if z is 9, right, so we go straight across, we're going to be spending $0 on the second part of our cost function, but we're going to face some marginal cost of z, which is going to be 8 times the difference in length of y as we increase z. So it'll be 8 times dy dz. Right? As we increase z, we lengthen y. As we lengthen y, we're spending $8 for every unit we add. So when we add 0.24, right, we're adding less cost than we're adding benefit. So it makes sense for z to at least be bigger than 0. Now, we've got to figure out questions like, how do we figure out what is dy dz? What is the appropriate length for z? So I'm going to start with kind of the messy approach here that I was stumbling on in class because it's got some kind of messy square roots. And that approach is to turn this all into one function where we're basically saying, let's just use z. We want to think about how do we convert total cost into some function of z. Well, that function is going to be, well, this part will be 9 minus z. Right? So part of our total cost is going to be 4 times 9 minus z. Right? That length, right, which is really just 4 times x, but we're getting rid of the x. We're going to put it all in z terms. Plus, we're going to have 8 times y. And what is y? Well, y is going to be the square root of z squared plus 2 squared. So 8 times the square root of z squared plus 2 squared. Well, 2 squared is just 4, so I'm just going to write 4. So now we've got our total cost in terms of z. And so our default approach here, especially given that we have access to computers when we're doing this, we'd say total cost prime with respect to z equals, well, this is a constant, 4 times 9, so we can ignore that, but we got a 4 times a negative z, right? So that's going to be, what, negative 4. Okay, let's just go ahead and write this out explicitly. So 4 times 9 is 36. 4 times negative z means we're doing minus 4z plus 8 times this mess. Oh, all right, here's where it gets tricky. We can't really split this apart, so this is just going to be plus 8 times that square root. All right, so minus 4, we've got that. d36 dz, how much does 36 change as we change z? Well, it doesn't. So I'm just going to ignore it. And then plus this other thing. All right, so what have we got here? I'm going to go ahead and rename some stuff. So I'll call it u. So I've got 8 times a function of u, and u is itself a function of z. So this is going to be plus 8 times the derivative of this times the derivative of the inside. All right, so what's the derivative of the outside? Well, this is the same as u to the 1/2, which turns out to be really convenient because it obeys the power function rule, which means we can say this is 8 times 1/2 times u to the power of negative 1/2 times the derivative of the inside, u prime. Right? And u prime, this is just another way of saying du dz. Assume that says du dz. All right, have we got everything? We've taken care of this. That's 0. This, we've got the 8 times some stuff. That's stuff. We've got some chain rule. Let's go ahead and find what u prime is. Well, u prime is just going to be, well, let's go ahead and write out u equals z squared plus 4. So u prime just equals 2z. So going back to tc prime, what have we got? We've got minus 4 plus 8 times 1/2. That's just 4. I'm going to simplify as we go. times u to the negative 1/2, which we can just substitute in z squared plus 4 to the 1/2 to the negative 1/2. Z squared plus 4 to the negative 1/2 times u prime, which is just times 2z. And we're going to make that equal to 0 and solve for z. So it's a little bit of a mess, but let's see what we get. Let's change colors just to make it stand out. It's changed already. All right, so let me start by simplifying a little bit. I've got a minus 4. I got a 4 times a 2z. Well, that's just 8z. Times this, which to the negative 1/2, we can just put that under our fraction here. So this is z squared plus 4 to the 1/2, right, which is the same as our square root. And we're going to say that this equals 0. Now the trouble we're going to run into is we want to get this z out. We want to find what is the appropriate value for z. So let's see what we can do. We can move that 4 over, so we can have this stuff equals positive 4. Let's go ahead and do that right off the bat. Positive 4. And then we can say 4 of this equals 8 of that. Let's see, or we could divide by 4 and we can say 1 equals some stuff. Let's do that. Let's give it a shot. So if I divide by 4, I'm left with 1. And this is going to put a 4 down here. So now I'm going to have 2z over this square root of z squared plus 4 equals 1. 2z equals the square root of z squared plus 4. All right, let's go ahead and square both sides. And then I think we might have a quadratic equation story. So you want to put both sides in parentheses just to be careful. Squaring the whole side means we're looking at 4z squared in this case. Equals, well, hey, this square means we can get rid of that square root, which means we're left with z squared plus 4. All right, this looks a little less terrible. Let's bring the z over. We're going to have 4z squared minus z squared equals 4. This turns out to be 3z squared equals 4. Z squared equals 4 over 3. And now we'll do a square root again, and we get z equals the square root of 4 over 3, which is the same as the square root of 4 over the square root of 3, which is the same as 2 over the square root of 3. Hey, that's not too bad at all. I actually kind of like that. It's not so bad when I do it right. I'm going to leave the light like that. At least, whatever. This will be fun. So we've got a candidate value of z, and even better than that, that corresponds with the answer that I've got right in front of me in my book, which is great. Now, as long as we're here, let's double check TC double prime. So here we've got TC prime, which we set equal to 0. So let's go ahead and just, in the margin here, we're going to look for TC double prime. How does this change as we change z? Well, that 4 is not going to matter. We're going to be left with this whole big mess, which looks like, well, we could either do it as a quotient rule or as a product rule. I'm going to take the product rule version of it. So what I want is ddz of 8z times this square root, z squared plus 4 to the negative 1/2. So I've got some product rule, I've got some chain rule. So we can call this G, we can call this H, And then h we can think of as having this other thing. So let's go ahead and find, well, g prime is easy. That's just going to be 8. H prime is going to be trickier. Let's find h prime. This is going to be negative 1/2 times z squared plus 4 to the negative 3/2. Right? We're going to subtract 1 from negative 1/2. So to the negative 3/2 times, oh, I should have done a different color. Let me make that explicit by changing colors now. Apologies if you are colorblind. I've switched to green, which doesn't help you, but it'll help me. Times the derivative of what's on the inside. Right? So this x is a times, it's not an actual x. So times this inside, which is just 2z. All right, now, the big question to worry about is going to be, what is the sign of TC prime? So we know that z, we've got a positive value. So this is going to be positive. This is going to be a fraction, right? Something over some positive number times some positive number. So we got a whole bunch of positives here. Right? So this positive, this is positive, and this part is negative. So h prime is negative. Let's go ahead and see what TC double prime is going to be. Can you see that all right? That's not great. Let me go to my dark green. There we go. That's better. TC double prime is going to be g prime h plus h prime g. All right, so g prime h, that's going to be positive. H prime g, that's going to be negative. So we are going to have to ask the question of what is the difference there? That's going to involve a little bit of arithmetic. That said, I'm just going to be lazy here and tell you that we are going to get a negative derivative here rather than spend time going through this. But this is a good practice exercise to take this derivative here and take a derivative of that function, get the second derivative and verify that it is in fact less than 0. All right, I'm going to stop here and I'm going to do a different video to show how Larry Gonick solves this.